This is Dr. Holt. In this problem, I have a 2.7 kilogram projectile. It's going to be fired with an initial speed of 122 meters a second at an angle of 29 degrees. So here's my projectile coming off the ground at 122 meters a second, angle 29 degrees off the horizontal. At the top of the trajectory, the projectile explodes into two fragments of masses 1.08 and 1.62. So here I've shown the two masses. At 3.69 seconds after the explosion, the 1.62 fragment lands on the ground, as shown here. It says, determine the velocity of the 1.08 kilogram fragment immediately after the explosion. And then on B, we want to find the distance between the point of firing and the point at which the 1.08 kilogram fragment strikes the ground. So it'd be more like, let me extend this on out. Grab this and clone this. So basically it's going to be kind of like this. Looking for this distance from here to here. And then C, we're going to determine the energy released in the explosion. Alright, to work this problem, I'm going to look at what takes place before exploding. I'm going to find my velocities, the components. So my initial in the x condition, or x direction, will equal to 122 times the cosine of 29 degrees. That'll give me a value of 106.70 meters per second. My velocity initial in the y direction will equal 122 times the sine of 29 degrees, and that gives me a value of 59.15 meters per second. Now note, the horizontal velocity is never going to change on this mass here, the 2.7, as it goes all the way up here prior to exploding. That's going to be constant. This will never change. Now the y value is going to decrease. It's going to decrease at a rate of negative 9.8 meters per second squared until it gets to the top, and at the top the velocity in the y direction here will be 0. Alright, so what we want to do on this problem first is try to find out what the height is. We want to find out what this distance is from here to here first, and we'll call that value h. Okay, so we'll go back to our kinematic equations, and we'll go back to the Vf squared is equal to V initial squared plus 2. We'll make that negative 9.8 times delta y. Now we're going to use this equation only in the y direction. Again, we know at the top it's going to be 0, so we'll say 0 is equal to, we use the 59.15, we square that, and then we'll just make this minus 2 times 9.8 times delta y. We move this to the other side, that gives me minus 59.15 squared divided by negative 2.9.8 times delta y. And if we solve using delta y, we will get delta y as 178.49 meters. Okay, so that's what the height's going to be here. So we'll go ahead and erase this right here. And we'll put in 178.49. Alright, now let's start working on what we know what's taking place here. Couple things. It says the 1.62 lands on the ground directly below. So we know if it lands directly below, it has no horizontal velocity. It only has a vertical component. We need to verify or determine what its velocity is going to be to reach the ground in 3.69 seconds. That's why it was important to find out what this height is. So we'll go back to our kinematic equations, and we'll make a determination of what that value is going to be. So we'll use the kinematic equation, delta y is equal to Vi in the y oops, sorry, times t minus 1/2 times 9.8 times t squared. Now we know our time, so we know our delta y too because we found it here. Now we're going to be traveling down, so we're going to make that negative 178.49 is equal to vi in the y times our time, and our time was 3.69 minus 1/2 times 9.8 times 3.69 squared. Okay, so now if we run that number and solve for this value here, we will find that the v and the y at the very top after the explosion, and again this is only for the 1.62, so I'll make sure I put that in for the 1.62 kilogram object, it's going to equal to a negative 30.29 meters per second. Alright, so that's going to be its velocity after the explosion. Now we can go back and start using momentum, and we can figure this problem out pretty quickly. Our initial momentum, and remember that's a vector quantity, is equal to the initial mass we had, which was 2.7, and again we're looking at what happens right prior to the explosion. It only has a horizontal velocity because again we've lost the vertical velocity at the top right here, so we take 1.067 squared. I'm sorry, 1.067, not going to square. Let me get that value down. 1.06. Okay. That's going to be our initial. I'll run that number and see what that value is going to be. So 2.7 times 106.7 gives me 288.9, and that's going to be in kilograms meters per second. Now note that that is only in the x direction, so I'll just make it an I hat. It's only an I hat direction. Alright, so what we know is PF after the explosion must equal to the same thing. Okay. Now we know also initially we had 0 in j hat in the y direction, so we know it must be 0 in the j hat afterwards too. Alright, so now we can find out what the velocities are going to be. We take the 288.9 kilograms times meters per second. We're going to set that equal to what our final is going to be. Now the only mass that we have going horizontally has to be the 1.08 because the 1.62 only has vertical velocity. So we come back 1.08 times velocity in the let's say x direction. We'll solve that, and what we will get would be that Vx is going to equal to, let me do it real quick here. Divided by 1.08. Thank you. Gives me 266.75. I'll put that in there real quick. Alright, and that's going to be in the I hat direction. And again, that is only, let me repeat that, that is going to be only for the 1.08 particle. Now we go back and we know that the PF in the j direction has to equal 0. We know what this particle has, so we're going to, and remember the vector quantity, so we'll take 1.62 times negative 30.29 plus 1.08 times v, and we'll make that vy. We'll solve for vy, and when we do that, that'll give us a value of 45.44 meters per second. And again, that's a j hat. So we can state that the velocity of the 1.08 is going to equal to 266.75 meters per second I hat plus 45.44 meters per second j hat. And that's how you get the velocity. Alright. Now while I'm here, I'm going to go ahead and figure out part C before I do part E, because it's just we have the velocity. It says determine the energy released in the explosion. Alright, so what I'm going to do is first time I'll find out what the actual, these are the components. Let's just find out what the velocity, do that in black. Let's find out what the actual velocity is going to be of the 1.08. Use Pythagorean theorem. Actually, I'll take out the vector because I'm not going to do the angle. Let's find the magnitude. That's going to give me 266.75 squared plus 45.44 squared. We take the square root of that, and we'll get a value of about 270.59 meters per second. Alright, so now let's find out if we've lost any energy. Alright, our kinetic energy. Okay, now again, this is going to be the kinetic energy prior to the explosion. So I'll say before explosion must equal to 1/2, and the mass of the particle that we had before was 2.7. Now remember, before the explosion I had 1.06 106.70 squared. That's how much kinetic energy I had. Kinetic energy after the explosion, that's going to be 1/2. I'll do this one first. That particle is 1.08. Make that better. Times 270.59 squared plus 1/2. And the other particle was what, 1.62 times this velocity, and we said that was 30.29. Again, make sure you put that in parentheses when you square that. So we'll run those numbers real quick. And let's see here. I take 0.5 times 2.7 times 106.70 squared. That gives me a value of 15,369.60. Alright, so run this number here. 0.5 times 1.08 times 270.59 squared plus 0.5 times 1.62 times 30.29 squared gives me a value of 40,282. So 40,282, we subtract 15,360, make it 370. And that gives me a value of approximately 24.9 kilojoules. So that's how much energy occurred during the explosion. Alright, now to do, that's part C right here. Now let's go back to part B. And part B says find the distance between the point of firing and the point at which the 1.08 fragment strikes the ground. Alright, so what we probably ought to do here is determine how far we went how far I traveled right when the explosion occurred. We can do that because we know we know what the initial velocity was, so we need to find how much time it took to get to the top. And go back to our kinematic equations. We had 59.15 was our initial. So let's just go back to VF is equal to VI plus 8T. We know at the top there was 0. We know again our initial velocity, run back up real quick, sorry, was 59.15 minus 9.8 times T. So run that number real quick. 59.15 divided by 9.8 gives me about a time of about 6.036. Meters, I'm sorry. Seconds, how about that? So we know our time. Now all you have to do is multiply that by our horizontal velocity. It tells you how far it went. So multiply that times 106.7. That gives me a value of 644. So let's scroll all the way down real quick on that one. So within that time, my delta x displacement would have been 644 meters. Alright, now, that's not the final answer, because what's happened is this particle, and this one we're looking for, has traveled that far in that time interval, but now it's being launched at a height, and it also has a vertical velocity. So we need to find out how much time it's going to take it to go back and hit the ground. So to do that, let's go back to our kinematic equation. We know if we go back to VF squared is equal to VI squared plus 2 times negative 9.8 times delta y, then we can find our final velocity. If I find my final velocity when it hits the ground, if I find my final velocity, can I not put it back into this equation and find my time? So let's try that. I'll go VF squared is equal to, now we know the vertical value was what? 45.44. Remember, the vertical is what's driving your time. 45.44 squared plus 2 times negative 9.8. And now we say, well, what is our vertical displacement? Well, that's just our height, 178.49. Now we make that negative because we're going down, 178.49. Run that number and we will get VF at impact. It's going to equal to negative 74.59. Remember, you're doing a square root. When you do a square root, you got to consider plus or minus. So it's going to be going down at negative 74.59 meters per second. All I have to do now is to take that value, put it back in, and find out how long it took for it to hit the ground. So I go minus 74.59 plus my initial, which is going to be my 45, minus 9.8 times t. We'll solve for t there. And we do that, we'll get 12.25 seconds. Alright. Now, all I have to do is take that time, apply it to the horizontal component of this, which in this case was the 266.75. So we do delta x 2 is going to equal to, I said, sorry, 266.75. Multiply that by 12.25. We do that to 66.75 times 12.25. That gives us 32.68 meters. So that's how many meters it's traveled since the explosion. Now the total since it was launched would equal to delta x would equal to delta x1, which we got right here, plus delta x2. So we take, that's equal to 644 plus 3268. We'll run that number real quick. 644 plus 3268. That gives me a value of about 3,912 meters, or 3.9 kilometers. And that's the answer to part B. Alright, very good problem. I like this problem a lot. It covers a lot of different things. So again, you're using your kinematic equations, you're using your conservation momentum equations, and you're also looking at kinetic energy. Alright, I hope this video helps you. Best of luck on future problems.